to any place. Then nobody question me. Oh, you took too long to to get a PhD. So I still try to learn that because when my time to sign a dissertation, I still feel, oh, should I sign or should I sign? So, so that's probably I still have to get a bit better learning from him. And Professor Boyd still at Stanford. So at my time, the complex optimization course, I think it's around 100 students, mostly EECS and more on signal processing control and so on. And he will tell you how large the class is. And so at Stanford, my training was, although we did hang-outs, but we were kind of really encouraged to also combine whatever you learn from theoretical, especially mathematical algorithms. So you probably know a lot of progress made by Stanford guys. So I think many people are trying to copy what made it so successful at Stanford, but I think it will be one of the secret ingredient that not many people out of Stanford know. So I think we are really honored to have Professor Boyd come here to give a talk. So let's give him a very big proud, and he will give you a talk for the next 1 hour.
tell them to turn that off.
Okay.
And just tell them to turn off the amplification.
Yeah. They need to record it through.
They can record it, that's fine.
Okay,
But
okay.
turn off the amplification.
Okay. So you know what to do there? Okay.
Actually, they don't because it's on.
Okay.
We'll just wait for them to turn that off. Do they understand this or not?
I probably know.
Okay. Can you explain it to them? It's not that hard, right? Can
Yeah.
you? All they have to do is just turn the
Yeah, I know.
amplification in
Yeah,
here off.
Yeah. Yeah.
Okay. I'll Yeah, so for actually, for teaching, it's fantastic, right? Because it means every week, students from, by the way, 25 different departments are solving problems in finance, signal processing, communications, these kinds of things, information theory. Okay, so here's CBX. This is, oh well, maybe it's 10 years old. Okay, so here's the mathematical description. And then this is written in terms of and this is written on top of MATLAB, and this would actually execute, right? And the idea is, if you know some MATLAB, or some of you may know CBX also, but if you know some MATLAB, this is completely readable here, totally readable. I mean, it just makes perfect sense, right? So the idea is that your mathematics and this thing looks very similar. So you can imagine it would be very easy to go from a mathematical description into a problem, into code that actually runs. Okay, so that was your whirlwind overview of convex optimization. The key is it's used in lots of different fields. It's also, if your problems are small and medium sized, it's relatively easy to actually just do it right now, because you use these high level languages and you don't descend to the level of, gradients and subgradients and line searches and all this kind of stuff, right? Because you don't have to, right? Any more than you write assembly language if you're writing a program now, which is ridiculous. Most people don't. Okay? What we're going to do now is we're going to look at these two more recent research topics in the area, and they're two different extremes, right? And the first one we're going to talk about is real-time embedded optimization.
Could we ask a question?
Yeah, of course.
In your lasso example,
Yeah.
how do we determine lambda
Oh, there's a great way to do that. Well, let's see, where is it here?
to get the
Okay, in lasso.
result?
So, okay, I won't find something good for it, but I'll tell you. There's a superb way to do that. You do cross-validation. So you take your data, you take 10% of it, you hide it away, you fit the model on 90% of the data, and then you check it on the data you've never seen. And that's an actual honest test, because you're actually seeing that you built a model on 90% of the data, it's never seen that 10%, so you're really checking what you want to use it for. And then what you do is you repeat that for different values of lambda. And whichever one gives you the best result on the test set, that's your lambda.
Okay. Is that part automated?
No,
No. Okay.
no, you do that yourself.
Okay.
Yeah, yeah. Yeah. By the way, in languages for statistics like R, that would be totally automated, right? On the other hand, it does require you, in this case it would cause, CBX doesn't do that. CBX just solves convex problems. Doesn't care if it's finance, image processing, data fitting, machine learning, it doesn't care, right? So to write that code, by the way, it'd be about like 5 or 6 lines, right? So it's okay.
Okay.
Okay, yeah. Okay. So the motivation is for real-time embedded is you have lots of applications where you have to solve the same problem many, many times, but with different data, right? So that's control. In control, basically you're solving a problem every sample point, but what changes are possibly the commands or the current state or something like that, right? Okay. In finance, this is the standard thing, right? You're solving a portfolio optimization problem it could be every second, every day, every 10 milliseconds, doesn't every week, but you're solving the same problem. And what changes is your current holdings, your estimates of returns, your estimates of transaction costs, these kinds of things. Those change all the time. And you solve the same problem, but with different data, right? So this is the idea. Now, this is actually used now. I mean, so supply chain, that's what they use. It's all embedded, right? So in chemical process control, that's been used since the late 80s. People have solved quadratic programs, convex optimization problems, to actually run chemical plants, right? In trading, it's been used. Long trading, like daily, it's been used. Here's what's cool. It turns out, and this is actually a very important thing. I hope you'll remember it. It's actually one of the few points of the talk. It's actually an amazing thing. It's something I didn't know 10 years ago. It's this. You can actually solve small and medium-sized convex optimization problems in milliseconds or microseconds. Okay? This, by the way, is going to change everything, I guarantee you. So we'll get into it, and I'll explain about this, right? So this is actually very important. Very few people know this. And I think very few people understand the implications of this for what's going to happen in the future of a lot of fields, right? Okay, so we're going to do an example. Quick example is let's do positioning. It doesn't have to be disk head. It could be any kind of high-end manufacturing process. So I have something. I'm going to apply a force, and I'm going to move this thing from one place to another. And I'm going to do this. I'm going to push it so hard that I have to model it with vibration modes, right? So that's why I have like 2 vibration modes here. Okay. So, and the idea is this is limited. Your force is limited, and you want to move it from one place to another. Oh, I should make a comment here, right? If you take a very classical course on the mathematical theory of optimal control, you'll hear about, Pontryagin's maximum principle and the adjoint and blah, blah, blah. Relatively, again, I'm sorry, relatively useless. I mean, it's interesting to get insights, but it's approximately useless. Oh, it's useful if your problem has 2 states, right? And some incredibly simple thing. Then you can use pencil and paper like the 19th century and get the solution, right? But I'm sorry, but that's not how engineering works now. Sorry. It doesn't work that way, right? So the point is, you could try on this thing. You can't solve this problem that way. I'm pretty sure you can't, right? Even if you could, you wouldn't want to see this. I don't think you could, so it's simple enough. Okay. So the modern approach is to look at this problem and say it's convex, period. That's it. You don't say anything else. You just say it's convex, and that's it. Okay. So here's an example. So this is the minimum time. This is this thing with three masses with springs, and you want to push it you want to push it from here over to here, and of course you have to apply a force, and then you have to brake, right? So turns out that's the optimal thing to do, okay? Right there. It's the global optimal solution. And it says, of course, you should push it, that's what this is, and you should brake, like here's some braking, right? Now, why all these weird wiggles? I mean, I can say what it is. You could say, oh, all this weird stuff, what you're doing is you're extracting energy from the vibration modes. You're doing active damping, right? But whatever. The point is, you cannot look at this and say, oh, I was just going to try that. I mean, there's no way, right? And then not only that, I mean, you could not, I mean, this is a simple problem. Now let's have 10 actuators, 27 states, and a whole bunch of complicated constraints. There's no way you can solve that problem. And definitely not with your Pontryagin maximum principle and things like that, right? I mean, there's just no way, right? This will work just fine, right? So this is the idea. It's not obvious. I mean, these are just not obvious things, right? Okay. So let me say a little bit about embedded solvers. You need things. They may have to be hard. They may have hard real-time deadlines, right? If you're embedding something in a control system, it has to execute in, let's say, 10 milliseconds, period, with no exception. It cannot run longer. You have to be able to know it will execute in 10 milliseconds, period. It has to have essentially total reliability, right? It cannot fail one time in 10 to the 6th, right? Because if you're running at a kilohertz, it's not going to take you very long before you hit a failure, right? And so you got to be able to handle things. You can't generate a floating point exception, obviously. You have to be able to handle poor quality data as well, gracefully. I mean, and a lot of things are out. You cannot, obviously, in a real-time embedded thing, you cannot do things like allocate memory. You cannot, go to the operating system and attempt to allocate more memory, right? You can't stop for garbage collection, right? I mean, so these are kind of obvious things, but nevertheless, it's different, right? So, okay. So most important is you need a small footprint, right? So it's got to be like statically, you have to statically compile it. You have to know exactly how long it's going to run and all that kind of stuff. So it's a bit different, right? And you sure can't use complicated libraries, right? And nothing that would use dynamic that would actually do that would actually allocate memory dynamically is completely unacceptable, right? So, okay. So if a general solver works, use it, right? For example, if you're doing trading and you have to calculate, if you're doing, let's say you're doing energy optimization, and you have 15 minutes or 5 minutes to decide, how much your storage device should either charge or discharge or something like that. If you have, that's fine, no problem. Just use a general purpose thing, it's fine. Otherwise, you develop custom code. You can do this by hand. That's good. Or I'm going to talk about doing it automatically via code generation, right? And when you do that, you can exploit the sparsity pattern and all sorts of other stuff. And you can do this at solver development time, not at runtime, right? And so here's what's weird. When you do this, and you do these kinds of things, you would expect a speed up that would be 10x. Of course you would. It turns out the actual speed up is typically 100x or 1,000x, and sometimes more, right? You might ask who gets the credit for that, and I can tell you it's not us. All the credit goes to the people who write the back end of compilers, right? So if you write something with a small footprint and you turn on GCC with an optimization level, or with a high optimization level, it'll take a while to compile, but once it compiles, you get something really fast, right? So they get all the credit as far as I can tell. Okay. So the idea is, so CVX does this. It takes a problem instance, it parses it, and gets the solution, right? If you do this sequentially, if you're doing if you're doing finance, let's say, then every single time you get a new problem, if you just change the coefficients, it reparses the whole problem and then solves it, as if it never saw anything like it before. And the difference is a code generator does this. You write a problem family description. The generator then generates like source code. You then compile that, presumably with a bunch of optimization flags on, right? And then you get a custom solver. And a custom solver maps problem instances into solutions super fast. Okay, so that's the idea. By the way, these are undergraduate CS ideas, except that undergraduate CS students don't know about convex optimization. But if they did, this would be undergraduate level, right? Actually, now at Stanford, some do, more than some. So here's an example of this. It's just to be proof of concept, right? Written by a student of mine, Jacob Mattingly. And it takes in a problem description and it generates completely library-free flat C source, right? So that's what comes out. Then my colleagues who do compilers love it because they can really show off, because it's almost branch-free code. It's not completely, but it's very close. And so for them, they just love it. This is exactly what their backends can optimize like beautifully. That's the idea. So this would be an example of the input description, right? So you might declare the dimensions, and this is, by the way, that's an SVM problem. And notice that the parameters, in CVX, the parameters are numerical. Here, they're placeholders, because these are not known until solve time, right? So what's going to happen is this is going to generate a C function, which when you compile, will do the following. You will pass a pointer, well, you won't, you'll pass a pointer to A and B. You'll call the solve method, and that solve method will write onto X, right, which will be it'll write onto W and V. There they are, right, the solution, right, and it'll do it really fast. These are like several years out of date, but it doesn't matter. Just divide everything by 5, and it'll be fine. So, but it does. The main point is something else. I'll say what it is. So this is a small SVM problem, and this is that disk problem, and it's kind of cool. Here's a problem with 60 variables, 100 constraints, and it's it's not bad. You can solve it in a quarter of a second. By the way, nowadays that'd be 50 milliseconds, right? When you actually generate code for that specific problem, you can solve it in 230 microseconds, and nowadays I think that's about 40 microseconds. So let me just stop for a minute and point out, because this is something very different. I actually gave a talk to a whole bunch of people who do optimization, and it was only about this one topic, about generating code. Throughout it, I kept talking about milliseconds and microseconds, and somebody came up to me afterwards and said, "Wow, that was a great talk." And he said, "But I have one question. What is a microsecond?" So wait. You shouldn't make fun of them. Now, wait. These are people who do operations research and finance. So guess what? Okay, if you do high-speed trading. But, look, if you do operations research, a microsecond is not part of your world, right? In fact, one guy said it's very simple. Their time resolution stops at about half a second. And I said, why? And he said, because if I can make an entry into an Excel spreadsheet and it'll update in half a second, that's good enough. There's below, any faster means nothing to them, right? Or I mean, that's not true. So the point is here, this is huge and scary. I'll say for my own field, I was in control, maybe I'm in control now, and the whole story about control went like this. At a very high level, control goes like this. Someone says, what do you do? And you say, well, I get 10 measurements from my airplane 100 times a second. And then I put out 7, and then I make, on the basis of those 10 measurements, I make 7 decisions. And what are they? And you say, well, I change slightly the control surfaces. I might change the thrust on the engines up and down a little bit. Yeah, that's what I do. And they go, oh, okay. How do you do it? You say, well, basically, we multiply by a matrix, right? I mean, it's true. Come on. This is about, okay, it could be a little bit more. I mean, you update a Kalman filter, but basically, you're multiplying by a matrix, okay? And then someone says, but look at these sophisticated people who do supply chain optimization. They do incredibly sophisticated things, much more sophisticated than multiplying by a matrix. How come you don't? And you go, well, they've got 10 minutes to do it. I have to do it in 10 milliseconds, and you couldn't possibly solve a complex problem. That's why we multiply by a matrix. Everybody following this? And I thought in control, this made total sense, and that's why I didn't have to worry about optimization. Because if you have to do something every millisecond, you can't solve an optimization problem. Guess what? That's like totally wrong. So, by the way, very few people get this. It's coming. I guarantee you in 5 or 10 years, this is going to take over a lot of control. A lot of people are very conservative, so it's going to go very slowly, but it's coming. A lot of things where people thought, you know, the reason we multiply by a matrix is because we don't have the time to do anything else. That's wrong. Okay, so this is going to change a bunch of things. Okay, yeah.
So the computing environment is just a regular, say, like the Intel i3.
Oh,
okay?
yeah.
And how about the, the operating system of those?
It generates flat C, so it'll compile to anything. So actually, this is out of date. I'm sorry, but I should have shown. We run these on ARMs now all the time and stuff like that. So even very low power stuff actually runs now.
Okay.
So with floats and stuff like that. So I mean, these work perfectly well on actually way sub-watt processors.
Okay.
Yeah. So yeah, we've done that. Actually, this is actually CVXGen is actually used now for a bunch of stuff, right? So okay. Okay, now we're going to shift gears. It's going to be the last topic. And we're going to go, instead of like solving small problems super fast, we're going to go to the opposite. We're going to solve gigantic problems, right? So that's the idea. So we're going to look at large-scale distributed optimization. And the idea is you want to solve like gigantic problems, just actually gigantic problems, right? You could even use the word like big data, although I think this is nonsense, but still, okay. So you could use the word, I mean, this is stupid, right? I mean, people who work with video don't say, oh, I have big data. It's like, I mean, come on, right? I mean, or what you do audio, and you go, oh, I'm getting, whatever, 5 megabits per second. You're like, I mean, they don't make a big deal out of it, but okay, I'll stop. Okay, fine. So you want to solve extremely large problems. And the fantasy is this. It does not exist now, but a bunch of people are working towards it. I mean, my group is, others are as well. What you really want is you want a CVX-like language. In fact, the ideal thing, and it won't be CVX because MATLAB is not really a language. You want a real language like Python or Julia, right? And so that's where this is going to happen. So you want to write a little tiny script in Python, run it on your laptop, try it with 10,000 variables. If you like what you see, if you don't like what you see, then it's game over. Then go do something else, right? If you like what you see for 10,000 variables, then what you want to do is the fantasy would be you'd actually find the solve method and you'd pass an option which says, please do it on a data center. So you want to be able to just fire and run the exact same code, fire up 10,000 cores, and solve it with some massive problem, right? This is the fantasy. Actually, I think it's going to happen. And it's going to be kind of cool when that happens. Okay, that's the idea. It's not there, but there's some actually good progress on that. Okay, so the key to that is distributed optimization. I'll go quickly over it, but it's actually good. If you haven't seen this before, it's really cool to get just the basic idea of what it is, right? the idea is, instead of solving it all with one, on one processor, right, you'll have multiple agents, and each of them will solve a problem, and then they'll exchange messages. And they'll have to do this iteratively, right? And by the way, you know, an agent could be a device, a processor, it could be a thread, right? It could be actually a separate entity, right? So you could imagine doing distributed dynamic power allocation or something like that, where actually these are different entities. Each one is responsible for its own power optimization, and then they talk to each other to optimize everything together. Okay, so this is the idea. Okay, and I'll speed up a little bit, but this is sort of the idea behind it. This is a baby example, but the idea is, suppose I want to minimize something which is a sum of three things. The first one depends on the first two variables. This is x1 and x2. This depends on the other two more, and this depends on the others, right? And so the idea is you want to solve this in a way that does this. One agent will be responsible for F1, one for F2, and one for F3, right? And then each one, and what will happen is they'll solve a problem related to F1, F2, F2, and then they'll exchange messages and repeat, right? So this is the idea. I won't go over the history. It has a very long history. Actually, everything does, but it goes at least to the 1950s for sure, right? Hilariously, at that time, in the 50s and 60s, they thought they could use these methods to solve a problem as big as, are you ready for this? 1,000 variables, right? Now we solve that now in about, I don't know, 500 microseconds or something, right? So, but that's not fair, right? You have to, if you propagate Moore's law backwards, you know, you do get an advantage when you've got a 10 to the 12 increase in computer power, right? So that is a little bit of an advantage. So, okay. I won't go over the history of it, but I will say this. There's a method called alternating direction method of multipliers. There's others. It's from the 80s, but actually it traces into the 50s, and it turns out it's very well suited to modern architectures. And I'll show that with one thing called consensus optimization. This is actually, if you want to know, this is sort of the most basic problem in distributed optimization. If you can solve this, you can solve many problems. So it's a good place always to start. And it looks like this. It looks really dumb. It's very simple. It goes like this. You want to minimize a function. You're going to choose x, and it's a sum of things, each of which is a function of x, right? So I have n of these functions, right? Now, of course, this is silly. You could just collect all the f's together and solve it or something, right? And if you want to think of this in a very specific way, think of it this way. X are the parameters in a statistical model. N are, I have servers where I have data, or, you know, so I have a petabyte of data at n places, like that. And what I want to do now is I want to find, let's say, the maximum likelihood estimate of these parameters. And so I would be minimizing the sum of the negative log likelihoods, right? So that's what this would be. And the idea is you do not want to put you don't want to ship all the data to one place and solve it. For one thing, you don't want to ship the data. And secondly, you probably couldn't solve it even if you could do that, because it would be too big, right? The idea is I want to do this in such a way that one agent operates with one block of data, right? So you put this in consensus form. It's very simple, and it looks weird, and it looks too simple, right? It looks like this. Here, there's a single common parameter. Here, each block gets its own opinion, called xi. So I have n servers, each sitting on a bunch of data, like the click-through data from yesterday. Each one is sitting on that. Then each one gets its opinion. That's called xi. And then you add a constraint that says everybody can have their own opinion, but they have to all be the same. That's what this says, right? So this is the idea, right? Now this is, if someone walked up to you and said, I'm going to solve this problem, you would immediately write it like that. So this doesn't look like progress, okay? But it turns out if you apply ADMM to this, you get something very simple and beautiful, and it looks like this. It says that in parallel, each of these agents should update their local opinion this way. You minimize fi, well, of course, plus, and then this term is what is used to coordinate them, right? And all the parts make sense. This says, please don't go very far. When you have bar, that's the average in the last round. This says, please don't move very far from the last average. And then you have this mysterious variable ui, okay? Then it says, calculate At the next step, each agent completely independently calculates its opinion minus the average of everyone else's opinion. This is the error. You want this to be 0. Then it says the new u should be old u plus this, and that says that u is the running sum of the errors. This is integral control. It is nothing more than integral control. Integral control is the sum of the errors, right? That's this. Okay. Now here's what's not obvious. Although this is a very intuitive algorithm, here's what's not obvious about it. It works always for convex problems. Always. No exceptions. Okay? And that's not like usually it works. It's just always. Okay? It's pretty cool. Okay? Now the statistical interpretation is super cool. It says that if these are negative log likelihood loss for this block, it means that we can actually do coordinated data fitting, right? Because everybody has their own block of data. And then what happens is that each round, what they do is they minimize their local loss function plus a quadratic. But a quadratic is actually nothing but, it's a Gaussian. And so it means that the only thing you have to implement is a Gaussian map method. And using that, we can actually cause all these things to converge to the global minimum, right? It's actually amazing that this happens, right? And it would appear in practice to be privacy preserving, although I have colleagues who work on privacy, and they say that this is not privacy preserving by some strict definition they have. Differential privacy. But I think as a practical matter it is, but that's another story. Okay. So we're going to do an example. We're going to do support vector machine. We're going to do a problem with 2 features. I mean, that's stupid. You don't need that. And we're going to do 400 examples, right? We can solve this problem in, I don't know, 30, 40 microseconds on a single thread. So you do not need distributed optimization to do this. This is just to illustrate, okay? So we're going to split the examples into 20 groups in an evil way. Each group, let's make it a spam filter. So each group of data is only going to have, all the data is either going to be all +1 or all -1. So for example, I'm going to chop it up into 20 groups. Group 7, every example they saw, everything was spam. Group 8, everything they saw was not spam, right? So by the way, from that point of view, it's very easy to fit a model. If I walk up to you and I say, please fit a model, and you go, please give me some data. And you go, here it is. Here's a whole bunch of data. And everything's -1. Then I can make a model for that right now. Ready? It's called return -1. There, that's my model, right? Oh, and it's very fast, right? So, I mean, so the point is, in this case, they have to coordinate to get a model, right? Okay, so, all right. So here's the way it works. Here's on the first iteration. This would be the true support vector machine classifier, right? These are all the original classifiers. Well, they're terrible. But of course they're terrible, because we gave each of these things a very skewed view of the world. So of course they're terrible, right? Now you run ADMM. After 5 iterations, it looks like this. And after 40, it looks like that. Now, what you want to understand about this is actually, to explain how cool this is, these are 20 boxes. Each one only sees 20 pieces of data. And very skewed data, like everything is spam, everything is not spam. That's all they see. Not one of them has even the slightest idea how many other boxes there are. They don't know. No one knows. There's no entity here that knows all the data. All that happens is, at each round, it says, here's my model, and then the central entity averages all the opinions, calculates the dual variable, sends a single number back to you, not a single number, a single vector back to you, and then based on that, you shove that in a prior and you recalculate, right? So the point is, here, this converges to the global estimate, even though no entity has seen the whole data. Nothing. Just to show you that this is sort of real, and you can actually solve real problems with it. I mean, here's just a quick example. I mean, this is also out of date, but it doesn't matter. It gives you the rough idea. It's a big lasso problem where it's not even that big these days. That's like 30 gigabytes of data. And you write, this is basically just pedagogical, just to show you can actually do this and it really works. And it's actually kind of cool. It takes you a significant amount of time to load the data. If you factorize, this is on 80 cores. If you factorize everything in parallel, that's all 80 cores going flat out. It's 5 minutes. And then the subsequent iterations are this, and then it takes about 5 to 6 minutes. By the way, This is least squares, that's lasso. Okay? So this goes back to the original idea that this nonsense about having an analytical solution being faster is, well, it's just that, it's nonsense. Not only is it nonsense, but it actually is an impediment to correct thinking, right? If you're always looking for an analytical solution which you then program or something, it's just the wrong way to do it, I think. So, okay. I should add, there's now multiple large companies whose infrastructure is now being loosely based on this, right, on consensus, right? So, because they have exactly this problem. You want to calculate a click-through model, and you have 10 major servers in some country. You don't collect all the data in one place. Each one of them calculates this. They run typically 10 iterations, and it's all over, okay? And they actually get a model based on all of the data. The data was never all collected in any one place. You couldn't even possibly do it. It's way too much. It's petabytes or whatever it is. Okay, so I'll just summarize. So the point is, a convex optimization, they arise in a lot of applications, and you can solve them very effectively. Medium scale problems, you just use CVX or CVX pi or something like that, right? If you do control or something like that, or signal processing, or something has to go fast, you can actually solve these at microsecond and millisecond time scales. That's not, very few people know that or appreciate it. And you can solve like super large scale problems using distributed optimization, and that's also coming, which is kind of cool. So, okay, so there's a bunch of references on this material. I mean, you just go to Google and type in anything related. But I do want to emphasize, I mean, there's tons of stuff here. Everything is there. Like almost all the, you'll find everything on GitHub, and for code, you'll find everything. I should say this though, don't get do not interpret this to think we did all this, right? This is the research of hundreds of researchers across many decades, right? So please, whatever you do, don't say, excuse me, what can your methods? Because these are not our methods. These are things that have been developed for decades by hundreds and hundreds of people. Okay, so I'll quit here.
About maybe 40 years ago, I was at Stanford sitting at you, scratching my head whether I should register or maybe I just audit it. As a matter of fact, I just audited the code.
That explains a lot.
Yeah.
Okay.
So I couldn't find a way to apply it and really, get my phone kind of, at least partially satisfied. But that also explains how effective what he was just saying. Any task you can grab and combine with your application. I think as an engineer, I really feel almost like 15 years still sitting. Some part is saying I'm still scratching my head whether I should join or not, join the effort or not. But I think it's probably a newer direction here. So I just say this just to feel free to add whatever questions you might think is stupid, but doesn't matter.
Yeah, anything is fine.
Yeah.
So I talked to many people who have never seen this before. Yes.
In page 40, what's
Yeah.
the end call? It like notebook call.
What is, what's MKL? Wait.
8 core. Because 10
Oh, 8 core. Oh, okay. Oh, this is 10 machines, each with 8 cores. Right? So total of 80 cores. You can't call it quad cores, twice of it. It's an oct core. I don't know what the name is.
And
Yeah.
page 20, why do they have two
20? Yeah.
Two vibration mode.
Oh, two vibration modes. Oh, so this is a linear system, right? And it's got 6 states, right? Because 3 positions and 3 velocities. And so the slang in mechanical engineering is you'd say, you know, it's like a rigid body with 2 vibration modes. It's just mechanical engineering
So
slang.
either have two damper. No.
Yeah, sure. But you would just say it's 2 vibration modes, right? Or that's how you'd say it.
And next page. Why? What about the waveform?
What's this?
Good. Because the waveform is so strange.
That's right. It's strange. That's right. That's the point. It's not obvious, right? So it's not obvious, right? Yeah. So we don't. What it is it's fast. This waveform will move that thing from one place to another the fastest. No one can do it faster, right? It is strange, but it's fast. There's another. Yeah. Yeah. No, it doesn't. Yeah, but I'll. Okay, so the question was, in many optimization problems, there are a lot of constraints. The examples we looked at, this had some, right? I mean, this has got this one right here, right? And this is imposed at every time, every moment in time, right? So actually, constraints do not complicate convex optimization problems at all. In no way. It's no easier, no harder, it's not a problem, right? Maybe in general optimization it is, but in convex optimization, constraints mean nothing. Doesn't matter. Yeah.
But it makes the dimensionality much larger, right?
So it turns out it makes the dimensionality larger. It turns out I'm glad you pointed that out because this is a surprising thing to say. It's at a very high level, but I'll say it. So it turns out, and I know because I was there too. You know, my original training was in math, and I didn't know that much. But it seems reasonable when someone tells you that a larger problem is harder to solve than a smaller problem. I mean, how else could it be, right? This makes sense, right? It turns out, and this is actually extremely important, so everybody should know this. It's a bizarre thing. It's this. If there's structure in the problem, that statement is false. It can easily be easier to solve a much bigger problem than a smaller one because of sparsity. So the secret, for example, of SPICE, the circuit, the integrated circuit, simulator, the secret was this. In the 50s and 60s, people at Bell Labs were trying to figure out how to choose the variables so that you solve the smallest number of variables you could, right? It was a disaster. And the correct thing to do, it happened at Berkeley, and it was very simple. Somebody just said, I got another idea. Let's take your circuit and let's write out all the equations they are directly from the physics. So a tiny problem that you would do as an exercise, with like 3 resistors and 2 voltage sources, you do that as an exercise by hand. A problem like that in SPICE generates something like 50 variables. Okay? But it's sparse, and therefore it can be solved incredibly fast. So in optimization, it's the same thing. So when you add, for example, this, once you take a course on convex optimization, you will find out that when you add this, you are adding many constraints and many variables, and the dimension is getting bigger. And guess what the effect is on the solve time? 0. Absolutely 0. This is strange, but it's true. Yeah?
Sorry, but sparsity is something that's inherent in the system of the problem.
That's right.
So the truth is that there's the sparse number of constraints that's factored in this.
That's right.
This problem. So that can get the
Right.
the quality of this possibly high.
Right. So as a practical matter, most constraints only involve a handful of things. Each of these constraints only involves the force at one time. It doesn't couple the two together, right? And so you do get sparsity, right? So I'm going to repeat my assertion. Constraints do not complicate it at all, like 0. In fact, that's the great part about it. The nice part about it is if you have an analytical solution and then somebody comes along and says, oh, add this constraint, it's a huge pain in the ass. I mean, you don't even have the analytical solution now doesn't work and you have to rework it and all that. For this, you're like, okay, no problem, fine. I'll just add them, and it doesn't have any effect. Yeah.
I guess this path engineering shows a perfect example to show the real-time control.
Yes, it's a perfect example.
Right.
Yeah.
How about because I'm the signal processing guy,
Yeah.
how about this kind of concept applied to digital signal processing
Ooh.
and image processing?
Yeah, great. So they're
Because I only see the one example in like conveyor sensing because for digital processing you can
So
reconstruct
there's-
the signal.
Mhm.
How about other application like you mentioned?
Yeah, so it's coming. It's actually coming, or in some cases it's here. Now, non-real-time signal processing, it's already completely pervaded by convex optimization, right? Because people will add L1 things. That's for non-real-time, right? But in fact, now it's coming to real-time, right? And there, you do the same thing you do in control. You'd have a sliding window or something like that, and you can actually solve these things. Audio is within reach right now. Other things are not. Can you do convex optimization on a gigahertz signal? No, not yet. But it's going to happen. I mean, I think that's clear. It's going to happen. Yeah. For anything non-real time, actually some image processing is now done this way, like total variation, denoising, other stuff. That's done at frame rate already. So it's going to happen, I think. I mean, I think it's just like control, right?
Right, something like an image restoration.
That's going to start happening. I mean, so these things, it's going to start happening. Yeah. Yeah.
I would like to know that do you allow industry to use ESPN to solve their problem?
Yeah, and they do. Yeah. Yeah, so several people, many are, it's actually in things right now, strangely, but yeah.
But can we do some operation, some optimization on image recount using patterns?
Yep.
If the virtual built-in optimization can help to do the global optimization.
That is a perfect example of where you would use distributed optimization. It's a perfect example. What you do is you take the image, you want to solve a problem on it, on the whole image, and you divide it up into 8 by 8 blocks by tradition or whatever. You divide it up into blocks, right? Now, each one, can solve for its block, but the problem is this boundary issues, and on the boundary, they have to communicate. And you would actually, ADMM would be a superb way to do this, and it's actually used. So that's a perfect example. Yeah.
So in this talk, you talk about lots of things that maybe are outdated or students shouldn't really hang up to them in school or something.
Mm-hmm.
So in your opinion, what should students learn nowadays? And that's the first part of the question. And I have a follow-up second part. In our experience, many of the students feel complicated in modeling their problem as convex optimization problems. And
Yep.
In your opinion, how do we facilitate the students in
Yeah.
this problem?
So those are great questions. So, and if I may forget one, in which case you come back and tell me. Okay. So the first one is what should students be learning? That's a great, and the answer would be linear algebra. This is very important. Computer science. And then, of course, between them is, computational linear algebra, probability and statistics, but not the boring usual statistics like, the p-value and all that. That's useless, right? That's totally useless, right? Okay. So, but just, actual, just basic probability and statistics, modern statistics, right? And then the last thing I would say is optimization. If you know those three things, linear algebra, right? Probability and statistics, modern statistics, and optimization, and you've actually done this in different areas. You could do image processing, you could do control, you could do finance, you could do signal processing, communications. Then you know a lot, and those skills will transfer to any of the other fields once you learn a new dialect. So actually, for students, it's a wonderful time because if you learn the right stuff, right, you can do MRI for your PhD dissertation or your master's or whatever you like. That's great. And if you get bored, you can go work at a social networking company. And then you get bored, you can found a company that does something. It doesn't matter. And a lot of our students do that. I mean, some still do the traditional thing, right? They do MRI, this kind of thing. That's fine. There's nothing wrong with that, right? But it's really cool. A lot of students do weird stuff, like they'll be at a wireless company, and then I'll see them 2 years later and say, "What are you doing now?" And they go, "Advertising." And I'm like, "Oh, okay." So you get the idea. So I think actually for students this is a fantastic time. Now there's a lot of other stuff that I don't think does need to be taught, but that's another story. Yeah. And then you had another question, which was
about modeling their problems as convex.
That's a great question. So I'm going to phrase your question in a much more aggressive way. I'm disappointed no one asked this question. I'm a little disappointed, okay? Someone should say, you know, well, yeah, come on. Like, you should say something like, come on, most problems are non-convex, right? And this is, by the way, that's a true statement, right? So, of course, and they'd say, well, I saw that, you say, I saw this talk about convex optimization. That's great, but of course, most real problems are non-convex. Okay, and that's true. Okay. Now let me tell you, now here's a response to that. So it turns out there's several things you can do there. So I teach a class on this, 10 weeks, they work 20 hours a week, they do serious work, and they come out fully trained in this. And it doesn't mean kind of this nonsense like they read a little thing or a 2-day short course so they know those terms and they wrote a little code. This is like they know it, we call it, they have working knowledge of it, street fighting knowledge, right? They can really do it, okay? Once you do that, such a person is unbelievably useful, especially for non-convex problems. And there's a couple of reasons for that. One way to do that is to approximate a non-convex problem as convex and then solve it. And actually, even when the approximations look absolutely terrible, the results are often, in practice, excellent. It's just bizarre, but it's true. So that's one way. So relaxations are like that, right? You look at a problem. So, and even when not, you can do things like sequentially doing it and stuff like that. So people who know this material are actually much more useful for non-convex optimization because they'll say, oh, that subproblem is convex, I can solve that easily. And then you focus on the other stuff. So that's a good question then. Yeah.
Okay. This is exactly the problem I was talking to you recently. We
Yeah.
should first complexify each like constraint.
Mm-hmm.
That's one approach. You make this almost complex function. You apply the complex fit to adjust your
Yeah.
programming to make the hash function different.
Yeah, you could do that.
One way
Yeah.
to solve it.
Yeah, actually, I'll give you a very good example. So the most simple example of non-convex constraints are Boolean constraints, 0, 1. That's the most simple one. I mean, here's an example. I want to schedule electricity generation for Taiwan for tomorrow in 15-minute increments. I mean, somebody does this, by the way, right? And there are integer variables, like this generator is either on or off tomorrow at 2:15 p.m. I mean, period. And there's rules about when you turn it on and turn it off and all that kind of stuff, right? Those are integer variables, right? So, and many key things have that flavor, right? These cannot be convex, right? So it turns out here's an incredibly bad approximation. Instead of, I'm going to approximate the 2-point set 0, 1, like off and on, by a number that's in between 0 and 1, right? And if you want an interpretation, you consider it like a quantum mechanical state, right? So if it's 0.3, it means you'd say, is generator number 3 on tomorrow at 2:15? And you'd go, I don't know, maybe with 30% probability or something. Anyway, it means nothing, right? It turns out, however, that when you schedule stuff, this is a standard method, and this works like amazingly well, right? There are methods that work better, but this works shockingly well. And you just do the simple thing. You solve it. Most of them, by the way, are either 0 or 1, meaning it's off or on. A few are going to be 0.3, and some are going to be 0.7. If it's 0.3, you just round it down to 0, and you say you're off. If it's 0.7, you say you're on. That's a heuristic, but the point is that the first step was convex optimization, and these methods work really well. Right, so.
That's another more important question.
Yeah.
Right now we have a multi-core CPU and
Yep.
discrete machines supposed
Yeah.
to be the main of them. But right now we seem to not have the internet advantage of using the program network.
Yeah. Oh, you do. Oh, you do. So the question was, can you take advantage of? Can you take advantage of multi-core stuff? The answer is sure. So there's several things. But it's not appropriate for embedded codes. But for larger ones, of course, you would do multi-thread stuff. But that's actually at the low level. That should just happen. And we have those now. So most interior point methods are multi-threaded. right? And they do take advantage of it. So we do have that, right? So that does happen. Yeah. Any more? Yeah.
Can we apply context optimization to the same like AlphaGo? Can we transfer this kind of problem to context optimization?
Yes, sort of. Yes, so actually there is actually reinforcement learning. I mean, basically, it's going to become, or it is, or will become, something like linear algebra, right? It's just part of the mathematical and computational infrastructure. So yes, actually a very common method is for reinforcement learning is the key is to make yourself a value function, right? So that it tells you what's the value of landing in this state, and then you explore a whole bunch of states out to see what it is. And in fact, often that value function is fit using some kind of convex optimization method, right? So it's not directly a convex optimization problem, but you use it, right? So it's like linear algebra or singular value decomposition, right? It's just part of the infrastructure. We all know it. We can use it, but it's just part. You use it with other things. It's very rare that your problem is a pure, eigenvalue problem or something. It's usually not a pure convex problem. Sometimes it's pretty close, though. So that's the answer. Yeah.
I'm a signal processing guy. Do you have a plan to small scale convex optimization or medium scale to digital synchrony?
Yeah, so there are some efforts right now. Actually, Google is working on this. Right. So there's something called the Halide language, and it'll compile stuff on all sorts of platforms. So you can run it like on a phone, and there's some connections. One of my students is trying to connect that to various solvers that we have, which will be very cool when it happens. It hasn't happened, but it'll be very cool. Yeah. Yeah.
Do you know about complex thinking?
Yeah.
One of the two offers.
So compressed sensing, how many people have heard about this or something like that? Okay, so, I mean, it's cool. My opinion of it is it's just a super duper special case, right? So I don't think of it as a separate field. It would be like saying, have you heard of regression or something? It's like, yeah. I mean, so for me, it's not a big deal. What I think much more interesting and important is the idea that I know how to make things sparse. And I can use that. If it's a least squares problem or something, I'm going to get compressed sensing, right? But the point is, I can do it in many other things. I mean, for example, I can do it in finance. Suppose you say, I want a portfolio that does something, it tracks something, some index, right? Then someone says, make it sparse. I know how to do that. And it's not compressed sensing, but that's a much more powerful idea, I think. Yeah.
Can you apply the convex problem for the robot?
For which?
Robot.
Robot. Yes. Yes, it's being done.
For the motor.
Yeah, oh yeah, no, for motor control and for robots, people are actually doing this. Yeah. There was a question up there?
How do you think about your neural network? How do you think about that?
About what? Oh, neural networks. Oh, great. That's okay. Well, we're going to make that the last question. I'm glad you asked it. No, it's not because you asked it. It's the last question. It's just because it's getting late. Okay. Yeah. So everyone here has heard about like deep neural networks, right? Okay. So, and you should know that when you fit deep neural networks, it's not a convex problem, right? By the way, they work really well. So you shouldn't ignore these neural networks. Convex optimization still plays a big role, right? These deep neural networks are used, you can think of them as things that will generate a modest number of excellent features. Then you use convex things on the top layer, which is actually what everyone does, right? So now, I mean, I think they're great. It's very complementary, these things, these ideas. It's something to know about. It's not as simple right now as it should be, and it requires you to have, let's say, 1 billion examples or something in a data center and a week to train it or something or whatever, or at least a pile of GPUs anyway, right? So, there are some disadvantages, but it's great, and I think it's complementary to this. This is simple, right? Or I should say this. Machine learning based on convex optimization is shallow learning. It's not deep. And actually, that sounds like an insult. It's actually not. It's really good. It's really simple. And what's amazing is how well it does being so simple. It's like least squares. Same story, right? So, okay. I lied. I'll answer another question if there is. Yes. What? I can't hear you from here. I'm sorry. Oh, sorry.
How does compiler make acceleration for large-scale distributed computing?
Oh, for large scale.
For large scale.
Yeah, so we've actually done that where we solve like big power problems, but each little problem is being solved by one of these CDX gen generated things. And the compiler then generates an extremely fast little thing to optimize, for example, the profile of one generator, for example, right? So you can do. Oh, that's a great question. I'm happy to say I have no idea how it works. My colleagues do that. I go GCC minus 03. Actually, I don't even do it. So here it is. My grad students edit a make file. And when they do it right and type make, it's much faster. There. So I don't know. I don't know. But all I can say is it's really impressive, and I really appreciate them. And actually, I presume most people here are consumers of this, not producers. Once a week, if you find a friend of yours who works on the back end of the compilers, just go up to them and thank them and say, thank you from the rest of us. We don't want to know what you do in detail, but keep doing it. Yeah. So I know, honestly, I really don't know. I mean, I know roughly, right? They rearrange code in such a way that they know it's gonna preserve the semantics, right? But what heuristics they use or how they do this, I honestly don't know. But boy, does it! And how do you get 100x? Don't look at me. I don't know. I really don't. Oh, that's a great question. How do you know a problem is convex, and how do you prove that it's? How do I prove what? How do you?
How to prove if a
Oh,
problem is convex?
excellent question. Okay, so all right, how do you prove That's a great question. So a very hard way is just to go back to the original definition and take x and y and theta and prove the inequality works. That's a disaster. The correct way to do it is actually constructively, right? You learn, and I tell you, this is how, if you want to learn this material, you can learn it very quickly. You learn about 50, or not even 50, like 20 basic functions, which are either convex or concave. You learn these basic ones. It's a short list. It's not hard to, after a while you know them, okay? And then you learn a very small number of rules for combining them. And that's it. Then, as long as you stick to those rules and that set, your problem is convex. And by the way, that's exactly how the software works. So once you learn those rules, you can actually use CDX, CDXPy, convex.jl. So that's a great way. So the answer is you form the problem in such a way that it must be convex. Can you do automatic parallelization? So people you can do things like that. It's not very sophisticated right now. Yeah. I mean, there's plenty of stuff to do, right? So, if you want to do that, please do it. It'd be great. All right. I'm going to declare that we have converged. Okay. Oh, one more, and then we're converged. Yes.
Start with, we need to be sure that the problem is solved.
That's right.
If it is not,
Yeah.
as knowledge people are
Right.
is it an art or science?
At the moment, that's a little bit, it's somewhere in between an art and a science. What happens when your problem is not convex, right? And Now, there are some interesting things to do. So here's one thing people do. This is insane. I'll tell it to you. If you have a constraint that's not convex, or a term in your objective that's not convex, you simply remove it. You ignore it. You just comment it out, right? So, by the way, that has a very fancy sounding name. It's called relaxation. Right? So what happens is, no, I'm serious. I'm not making this up. So what would happen is, someone says, "What are you doing?" And the answer is you're actually ignoring a constraint, and then you dress it up with this fancy mathematical thing. You say, "Oh, I'm forming the convex relaxation." And it's supposed to sound sophisticated, but actually all you did was you commented out the things you can't handle, right? So here's the weird thing about convex relaxations. There's a long history of them, and they work really well often, like shockingly well often. So, good.
I think it could be
I mean, there are interpretations of relaxation, but what I can tell you, and probably most important, is just as a practical matter, you should not be afraid to apply a relaxation because these things work really well. And they've been discovered and used in many, many fields outside of this, like in power systems it's used in other areas. And they may even not know that word, that field. But many people do this, and it often works. Okay, great. Cool.
So,
I think we're done.
Good.
Great.
I
Okay.
think we try to get everything done by perfect time.
Okay.
So, we are working on inviting Professor Boyd to visit NTU more often lately. So I hope to see you quite often here.
Good.
And let's thank Professor Boyd last time during his history. Okay. Thank you.